Here we are sitting in the thermal laboratory of ESTEC. We have a lot of vacuum chamber where we are able to go from minus 250 and up to plus 200 and even more. And a lot of JUICE hardware has been qualified here, or thermal performance of the hardware has been tested here. JUICE is very special because on the way to Jupiter we go much closer to the Sun than the Earth is, and we have this Venus flyby. But in very beginning of this year, 1st January, we went even closer to the Sun with what we call the Sun closest approach, and we had 3,320 watts per square meters of sun flux. So that's more or less 2.5 times more than on Earth's vicinity. So the thermal control has to face both this very hot environment but being able to withstand the mission in the very cold environment. On JUICE we have a huge antenna. The size of the antenna is meant for communication from very far away to the Earth, but it's located on the side of the spacecraft where during all the cruise in the inner solar system, that is between Earth and the Sun, close to Venus for example, we use it as a thermal shield to shadow the large part of the platform. Venus is fully covered with white cloud, and it reflects 80% of the sunlight, which means that when we pass between the Sun and Venus, the spacecraft will have all this reflection of solar flux from the backside. That's a bit unique that what happened during the Venus flyby. We have here 2 years of temperature measured on the JUICE high-gain antenna, starting really from launch, 20 degrees in Kourou. And then we have a first approach from the Sun, then come back to Earth flyby. And in 1st of January, we experimented our Sun closest approach, where we reached temperature slightly above 150 degrees. And now we are going to be a bit slightly warmer with the Venus flyby. But for us, we have already experimented the hottest temperature possible on JUICE, and particularly on the high-gain antenna. JUICE is completely surrounded by these blankets.